The next speaker is Andy O'Bannon, and he's going to talk about the central charge of self-dual strings from holographic entanglement entropy. Please.
Okay. Hi, I'd like to thank the organizers for inviting me to speak. This talk will be based on work in progress with John Estes and Darya Krim, who are in Brooklyn, and Brandon Robinson, who's a postdoc in Southampton, and my student Ronnie Rogers, also in Southampton, and Darya and Ronnie are both in the audience. And I'll warn you, this is work in progress, so I'm going to present some results we have, and we welcome any feedback that you might have. I'll also warn you that I normally do applied holography, but this is going to be more theoretical because the topic is, oh, that's not supposed to be there. The topic is M-theory. So back in the second superstring revolution, we learned that all the 10-dimensional perturbative string theories are related by dualities. And furthermore, they appear to be limits of a more fundamental 11-dimensional theory called M-theory, whose low energy limit is 11-dimensional supergravity. And a lot of what we know about M-theory comes from supergravity, which is actually a pretty simple theory. So this is the bosonic action of 11-dimensional supergravity. The only bosonic fields are the metric, which has an Einstein-Hilbert term, and then a 4-form, which has a kinetic term and a Wess-Zumino term, where C3 is just the potential for F4. And you can do an 11-dimensional Hodge duality to get F7 and write that as D of C6. And so the existence of the C3 and C6 tell you that the stable solitons of this theory are M2 branes and M5 branes. And these are my crude pictures. So the M2 branes will be yellow rectangles, M5s will be green. So M-theory, or supergravity, is not a theory of strings, it's a theory of membranes. So if you want to study M-theory, you want to know as much as you can about these M2s and M5s. Relatively speaking, a lot is known about the M2s. So if you ask what's the world volume theory on n coincident M2 branes, it's called the ABJM theory, after Aharoni, Bergman, Jafaris, and Maldacena, who were building on work by Bagger, Lambert, and Gustafsson. It turns out to be a 3-dimensional n equals h superconformal Chern-Simons matter theory, where the gauge group is UN level 1 cross UN level minus 1. In other words, there's two Chern-Simons with levels 1 and minus 1. So it's special, it has a lot of supersymmetry, but it is just a conventional quantum field theory at the end of the day. And so we know a lot about M2 branes just doing calculations in this theory. You can also take a Maldacena limit where n goes to infinity, and then the holographic dual of this theory is 11-dimensional supergravity on ADS4 cross F7. And we know a lot about the theory from that description. But if you ask the same question about M5 branes, so M coincident M5 branes, much less is known. From supergravity, we know a number of properties this theory should have. So it should have 6-dimensional n equals 2, 0 superconformal symmetry, which is the maximal amount. We believe it has some gauge group UM. However, the only irreducible massless representation of 2, 0 supersymmetry is called the tensor multiplet, which has 5 real scalar fields. Those just describe the positions of the phi branes in these transverse directions. And then the fermionic superpartners, and then to make the number of bosonic and fermionic degrees of freedom the same, you need a self-dual 2-form field. So in other words, the world volume theory has this 2-form A2 with a 3-form field strength. And then under the 6-dimensional Hodge duality on the world volume, it's self-dual. And this self-dual 2-form is the main reason why it's difficult and maybe impossible to write a Lagrangian for this theory. First of all, it's difficult to generalize gauge transformations when your gauge field is a 2-form instead of a 1-form. And furthermore, it's self-dual, so you encounter a lot of the problems you always have with writing Lagrangians for self-dual fields, at least Lagrangians with the properties you want, like locality, Lorentz invariance, and so on. And indeed, some people say these are non-Lagrangian theories. Furthermore, but anyway, the point is they're very special and important. One reason is that superconformal quantum field theories can only exist in dimensions 6 or less. And that's for just group theoretic reasons about the algebra of the superconformal algebra. So this is living in the maximal dimension where that's possible. It has no known free parameters besides M. So there's no marginal coupling. You don't get to choose a number of flavors or anything like that. You just pick one integer M, and the theory is completely determined. People also argue that you can't reach this theory from an RG flow where the UV fixed point is a free theory. So they call it an isolated fixed point. So altogether, this tells you this theory has a lot of uniqueness. It's a highly symmetric theory in this sort of maximal possible dimension. And so there's some idea, you can't really prove this, but there's an idea that maybe it's a master quantum field theory that you could derive all other quantum field theories from, for example, by compactification to lower dimensions or introducing relevant deformations that break supersymmetry, et cetera. So even if you're not interested in quantum gravity, if you're just interested in quantum field theory, you should be interested in M5 brains. It's very difficult to study. A lot of what we know about it comes from the Maldacena limit where M goes to infinity, because the holographic dual is known. It's 11-dimensional supergravity on ADS7 process 4. And more recently, people have done bootstrap, which seems to be working and telling us about it. But the way we're going to study this theory is using the following observation, that M2 brains can end on M5 brains. So here's the intersection, this quarter BPS intersection, where the M2s and M5s intersect in 1 + 1, and then the M2s have one transverse direction. So you can view this either from the perspective of the M5 brain theory or the M2 brain theory. So from the M5 brain point of view, this looks like a 1 + 1 dimensional soliton, or in other words, a string that's charged under the 2 form. Furthermore, if you take the 4 directions transverse to the string, write them in spherical coordinates, and then consider an S3 surrounding the string. So its electric charge would just be the integral of star of F3 over that S3. But because F3 is self-dual, that's equals to the integral of just F3. So in other words, the electric charge of the string is equal to its magnetic charge, and that's why it's called a self-dual string. And furthermore, it obviously is going to break some of the symmetries. So here's the bosonic symmetry of the M5 theory. So there's the conformal group, SO6, 2, and the R symmetry, SO5, which just rotates the 5 transverse directions. And just looking at this picture, you can see this will obviously get broken to SO2, 2. That's the subgroup that preserves the position of the string. Here, I'm assuming the string is just straight. So I have translation invariance along the string. And then there's 2 SO4s, which are just in the 2 through 5 directions and the 7 through 10. And on the string world volume, those act as R symmetries. And these 2 R SO4 symmetries tell you that in the 2-dimensional point of view, from the string point of view, this is a large 4, 4 superconformal symmetry, as opposed to a small 4, 4, which just has a single SO4. This symmetry will be important. So from the M2 brain point of view, or the ABJM theory point of view, you're just taking ABJM theory and introducing boundaries, but you have to be careful to preserve the right amount of supersymmetry. And that took people a few years to figure out. The state of the art is this paper by Yorkus from 3 years ago, where he writes down explicit formulas for the boundary terms you have to add. And also you have to add some massless, 2-dimensional massless multiplets at the boundaries to get the right symmetries. But otherwise, from the M2 brain point of view, you break to the same symmetries that you expect. You start in a different place with the 3-dimensional conformal group and an SO8 R symmetry, but you break to the same symmetries, which you can also see from this picture. You're just the 8 directions transverse to the M2s, you're breaking to SO4 and SO4. So back to the M5 brain point of view, the tension of the self-dual string will be proportional to the M2 brain tension times the extent of the M2 brains in the transverse direction. And so what I'm going to do in this talk is consider the limit where the extent is infinite, so that the string tension is infinite. And in that limit, the string is not dynamical. It becomes instead what's called a Wilson surface. This is in analogy with Wilson lines of Yang-Mills theory. So schematically, you should think of the Wilson surface operator as something like this. So it's the trace in some representation of the group of the exponential of I times the integral of the 2 form. Oh my God, what's happening? Okay. This is the integral of the 2 form over the world sheet of the string. And then there are additional terms to make this supersymmetric. And just to be clear, so the representation will be specified by some Young tableau of the group. So a central question about self-dual strings is, what is their central charge? This is a really important number that characterizes these strings, in part because it counts the massless degrees of freedom that live on the self-dual string, which in this intrinsically interacting theory is not immediately obvious. In particular, you want to know this central charge as a function of the number of M5 brains M, the number of M2 brains N, and the representation R. And as far as I know, there's only 2 papers that have explicit results for this, one by Berman and Harvey from 2004, and one from Yorkus and Santos in 2012, which gives you some idea of how hard it is to do these calculations. However, in the last 5 or 10 years, a number of 11-dimensional supergravity solutions have become available that describe Wilson surfaces holographically. by Dover, Estes, Gutperl, Krim, Feldman, and Bacchus. Gutperl and Krim are both in the audience. In particular, they are 11-dimensional solutions that have the isometry you expect for a self-dual string, and they, roughly speaking, they come in two classes. There are asymptotically locally ADS4 cross S7. These describe ABJM theory with the boundary. And there's also ADS7 cross S4 solutions, which describe the M5 brane theory with the Wilson surface inserted. So the goal for the rest of the talk will be to compute the central charge of the Wilson surfaces, that is a self-dual string with infinite tension, using these supergravity solutions. But before I do that, I have to tell you what I mean by a central charge. Right, so the outline for the rest of the talk, we're going to use entanglement entropy to get a central charge. So I'll describe that, then I'll talk about the holographic duals, not in much detail, and then I'll present our results for the central charge. So when people say central charge, usually they think of a 2D CFT, and in 2 dimensions, the conformal algebra is the Virasoro algebra, which has an infinite number of generators, and there's a central extension term whose coefficient is the central charge. But then the central charge shows up in many other quantities, like the trace anomaly, entanglement entropy in the vacuum of the CFT for an interval of length L with some cutoff epsilon. Shows up as the normalization of the stress tensor 2-point function. It shows up in the thermodynamic entropy, and in fact, in other places as well. However, we don't have a 2D CFT. We have a 2-dimensional conformal defect or boundary in a higher dimensional CFT, which means in general, we will not have a Virasoro algebra, so we can't define the central charge that way. So just to be a little more explicit, we're starting with a conformal group in higher dimensions, which has a finite number of generators, and then we're breaking to a subgroup. So generically, we will not have the Virasoro algebra. However, we can still ask, well, a lot of questions come up, like what are the forms of all these other things? Are they still related to each other in the same way? Whoops. A lot of that is unknown. Some of it is known. So for example, the form of the trace anomaly is known, and Chris Herzog wrote that in his talk. But the definition we're going to use, so we have to go find some other definition, and we're going to use the entanglement entropy. So how do we do this? So in the M5 brane theory, so to compute the entanglement, we fix a time slice. So the space will be R5. So here's my world volume of my M5 branes. My self-dual string is this line, and then our entangling surface will be a sphere of radius L, which is this yellow disk. And when we do the calculation, what we find is perhaps not surprising. The entanglement is a sum of what looks like 2 terms, the result for the 6D CFT, and then a result that looks like a 2D CFT. The 6D result looks like this. There's the area law term, which goes like 1 over cut off to the 4th. There's a 1 over epsilon squared term. These have non-universal coefficients. There's a log term whose coefficient is proportional to the central charge of the 6D theory, central charge A. There's a non-universal constant, and then terms that vanish as epsilon goes to 0. But then on top of that, we find additional contributions, a log contribution and some constant contribution. And so to define a central charge, what we do is we take this result, we subtract off the 6D CFT result, so this first line, and then we want to pick out the coefficient of the log term, so we take L times DDL, and then there's a factor of 3 for the normalization. So to put it more simply, we compare the CFT without the Wilson surface to the CFT with the Wilson surface, and we calculate the change in the coefficient of the log term. And then from in the ABJM theory with the boundary, it's a similar story. So at a fixed time slice, we have R2, but with the boundary. And our entangling surface will be a semicircle of radius L. The entanglement, again, splits up into what looks like half of a 3D CFT results. It's a half because, intuitively, because we cut off half of the space, plus a 2D result. And we do a similar subtraction to extract the central charge. And so that's the definition that we're going to use. And I'll just say a few words about how we calculate it. So as I mentioned, there are these supergravity solutions describing Wilson surfaces. So they have the isometry you expect, SO2, 2, and a pair of SO4s, which means on the gravity side, you'll have an ADS3 and 2 S3s. Whoops. And then similarly, there are also asymptotically ADS4 solutions that will also have ADS3 cross S3 cross S3. And so what these people do is they write the most general ansatz that has those symmetries. So here's the metric. So there'll be an ADS3, a pair of S3s, You have two more directions, which you can package into a Riemann surface. And then a priori, you just write some arbitrary functions in front of these, f1, f2, f3, and rho. And so you get and you do the same thing for the 4 form. And so you get a geometry that looks like ADS3 cross 2S3s fibered over a Riemann surface, and you then take that, plug it into your BPS equations, and try to solve them. And as I said, there's these two solutions that have different asymptotics, which describe either the M5 brane theory with the Wilson surface or ABJM with the boundary. And the only other thing I'm going to say about them is that if you want to know how many M2s and M5s you have and where they are, you have to look at the singularities of these functions. They're functions over a Riemann surface, and so they'll have poles of different types. And you can figure out how many 4 cycles you have, how many 7 cycles. You can integrate F4 and F7 over those. And get the numbers of M2s and M5s, and also the representation. Of course, we use Ryutaki-Yanagi, so we have to compute the area of the minimal surface that approaches our entangling surface at the boundary, and then divide by 4G. And it's a 2-step process. First, you have to find the minimal surface, which means solving some differential equation, and then you have to compute the area, which means doing an integral. I think my main contribution to this field was in this paper with Jensen, Christian Jensen, where for actually any holographic system with a conformal boundary or defect, we solved for the shape of the minimal surface that approaches a sphere at the boundary. So half of the problem is done, but you still have to do the other half. You have to compute the area, and in these coordinates, it looks like this. And I should say this y is the holographic coordinates of the ADS3. Just in Pfefferman-Graham coordinates. But anyway, this is the integral that actually my collaborators mostly have done. And then you have to go and do the subtraction that I mentioned to get the central charge. And I should mention that for the asymptotically ADS7 solutions, most of the work was already done by Gentle, Gutperl, and Marizanu in 2015. They just didn't write their answer in terms of numbers of M2s and M5s. So we are going a few steps beyond them. So that's all the sort of technical stuff without going into much detail, but what's the result? We can do this for an arbitrary Young tableau, but we parameterize it in a sort of funny way. So let me explain. So we'll have a set of numbers MA, which will be so any given MA will tell me the number of M5 branes that have NA M2 branes ending on them. Okay, so in other words, we have to specify 2 sets of numbers, the NA and the MA. And to give you an example of how that works, so in this picture, N1 would be 1, 2, 3, 4, 5, 6, 7, 8, because each box represents a single M2 brane. So N1 would be 8, M1 would be 3, which is just telling us we have 3 rows of this Young tableau that have 8 boxes in them. And then N2 would be 6, and M2 would be 2, and so on and so forth. So we have to specify these 2 sets of numbers where the set NA is ordered from largest to smallest. Up to some value, big N sub little n. It's not the best notation, but big N sub little n. And so then the total number of M5 branes is just the sum of the MA, and the total number of M2 branes is the sum of MA times NA. And there is one subtlety in that there can be M5 branes that have no M2 branes ending on them, which is why A runs from 1 up to add those in your count of M5 branes. Okay, so with that parameterization, I can now show you our results. So for an arbitrary Young tableau, these are the results. So for the M5 brane point of view, or the asymptotically ADS7 solutions, it looks like this. 3/5 times 8mn plus n squared over m, sum on A of 8ma squared na minus ma times na squared minus 16, sum on B from 1 to A, Na, Ma, Mb. And then from the asymptotically ADS4 solutions, it's 3 times the sum on A minus Ma squared Na plus a half Ma Na squared plus 2 times sum on B, 1 to A of Na, Ma, Mb. So not terribly illuminating. One thing I'll mention is that they don't agree, they're not identical, and they don't have to be because it's the same quantity computed in different limits. So the ADS7 solutions, you can actually send the number of M2 branes to 0. And if you do that, you'll just recover exactly the ADS7 cross S4 solution. Whereas for the ADS4 solution, you have to keep the number of M2 branes big to stay in the supergravity limit. And also, you can't send the number of M5 branes to 0 in that case, because if you take away the M5 branes, then the M2 branes have nothing to end on. So they don't have to agree. But these are not very illuminating, so to get some idea for what these are telling us, we'll look at some specific representations. So let's start with the M fibranes in the anti-symmetric representation. So in our parameterization, this means N1 is 1 and M1 equals N. But anyway, this is what you get. So you get the 3/5 8mn plus n squared over m minus 8n squared minus n. So first thing I'll mention, there is a quick check you can do that if m equals n, then this vanishes, which you can see just by looking at these coefficients. And what that's just saying is if my gauge group is um, and I have an anti-symmetric representation with m boxes, that's a trivial representation, so my central charge had better vanish, and indeed it does. Is there any physics in this? Well, this is what we're studying now. The first thing you observe is that you don't see the characteristic m cubed of M fibranes, which is supposed to, for example, the central charges of the M fibrane theory at large M would go like M cubed, but you don't see that here. Although you can technically, if you scale M or scale N as some power of M, you can force it to look like M cubed. Also, you don't see the n to the 3/2 that you would expect for the M2 brane theory. Instead, you're getting a bunch of terms that are essentially quadratic or linear in M and N. And then for the symmetric representation, well, it looks almost the same, except the factor of 8 is now on a different term. It's switched from the n squared term to the n term. And then if you ask the same questions about the M2 brane theory, or ABJM with the boundary, so starting with the anti-symmetric, you get this, 3 times n squared plus 1/2 n. The first thing you observe is that there's no m's here. And there's a reason for that. It's because the M2 branes know that they're ending on M fibranes, but they don't know the total number of M fibranes. Because there can be, as I said before, there can be M fibranes that have no M2 branes ending on them. So you actually can't write this result in terms of the total number of M fibranes. Otherwise, it's just telling you, well, somehow the number of degrees of freedom scales like n squared with some subleading n. And then the symmetric representation looks almost the same, except the factor of 1/2 switched to the first term. So if I toggle back and forth. Okay, so those are some of the results. And so what we're doing now is we're trying to compare to the previous calculations. So I don't know how much time I have. Oh, good. Okay, so I can go through this. So there was first Berman and Harvey in 2004, and they used anomaly inflow techniques to get a fully non-perturbative answer. And in particular, they were doing this calculation somewhere on the Coulomb branch. So in other words, they had stacks of M fibranes, but the M2 branes had a finite extent. And the answer they get, they write in this form, 1/2 n times some number alpha, where this number alpha depends where you are on the Coulomb branch. And so the two explicit examples that they present, one of them is if you separate just a single M fibrane, so that the group goes from UM plus 1 to UM cross U1. In that case, you find this goes like 1/4 n times M. And that doesn't look exactly like anything that we found. If you compare to the M5 theory, we did have terms that go like M times N, but with a very different prefactor. However, this does, so it doesn't quite agree, we think. However, we're not sure that it should agree for two reasons. One is that we sent some of our M fibranes off to infinity, so we have semi-infinite M2 branes. We're not sure how important that is. More importantly, we're not sure, from our point of view, we have to specify a Young tableau. So we have to say which M fibranes is each M2 brane ending on. And in their paper, it's not clear what Young tableau or what representation they have. And we talked to David Berman, and his guess is it's the symmetric representation, but as I mentioned, that doesn't agree. They also considered completely breaking the group. This should say UM. This should say UM breaking to U1 to the M. So separating out the M fibranes completely, so they're all separate. In that case, they found 1/8 times n times m squared plus m minus 1, which again doesn't look like, really look like any of our results. And again, we're not even sure if we should be comparing something like this to our case. The other calculation that I mentioned was Yorkus and Santos. They used blackfold techniques to calculate the thermodynamic entropy. of the system, and you find something that looks like M5 brane theory entropy plus M2 brane theory entropy, but then at the intersection you find a term that looks like, at least it's linear in T, so it looks like a Cardy entropy of a 2D CFT. And so they identify their central charge that way, and the result they get looks like this, with this strange number in front, 8/45, and then some gamma matrices, gamma functions over root pi, times an n squared over m. Numerically, this is about 1.5 times n squared over m. And we do get a term that goes like n squared over m in general, so say in the symmetric representation, anti-symmetric, and in fact in the general formula, there is an n squared over m. But our coefficient does not agree with theirs. And again, we're not sure that it has to, because this is a thermodynamic entropy. And as I said before, with the two-dimensional defect or boundary, it's not clear that the central charge you get from the entanglement should agree with what you get from the thermodynamic entropy. And additionally, we're not sure what representation they're studying. Again, in terms of Young tableaus, it's not clear. But there is a very revealing, okay, so we have this ugly form for our most general results. And for the M5 brane case, there's actually a very nice way to write this compactly. So if you introduce the highest weight vector of the representation, lambda, and then the Weyl vector rho, you can show that this form can actually be written like this. So it's the projection of the highest weight vector onto the Weyl vector times a factor of 16, and then minus the norm, I guess the norm. And then we still have our overall 3/5. So there's a nice compact way to write it, purely in terms of group theory data. And this is basically where we are right now. There's one more thing that I want to say so you can ask, what is the meaning of this object? We have found one other case where a very similar form appears, namely in a 2D CFT with WM symmetry. Okay, so it has a central charge of this form, which you can write in terms of m, the norm squared of the Weyl vector. And then there's a parameter called q, which is called the background charge. In the corresponding Louisville theory, or I guess Toda theory, this controls the coupling to the Ricci scalar. But anyway, a theory of this type has chiral primaries of a dimension whose form looks very similar. So they're chiral primaries that are labeled by these highest weight vectors, or labeled by representations. And their dimensions are precisely of this form, but with two differences. First, there's this parameter q appearing here, and also there's a factor of 1/2 instead of 3/5. And so it looks like what we're getting is basically this type of dimension where q is equals to 8, and then for some reason that I don't understand, we're getting a different prefactor. But what this really tells me is that we can probably explain this form of the results using the AGT correspondence. So in particular, one way to think about AGT is taking M5 branes, wrapping them, or compactifying two of the dimensions on a Riemann surface, and then in the remaining 4 directions, you'll get an n=2 supersymmetric theory. And if you then introduce a string-like defect in that 4D theory, well, okay, AGT is then the statement that a certain class of BPS correlation functions are equivalent to some correlators of a 2D Louisville or Toda theory on the Riemann surface. And in particular, if you introduce a string-like defect in the 4D theory that appears in the Louisville description via the AGT correspondence, it appears in the Louisville description as the insertion of a chiral primary. And so our guess is, well, that chiral primary has this dimension, although we're not sure why this is showing up as a central charge. As I said, this is work in progress, and so this is where we are right now. And so that's it. So I guess I don't need to say the summary. This is all the stuff that we did. I'll just mention that in the future, we think we can make comparisons to other calculations. So there are calculations of the elliptic genus of M2 branes between separated M5 branes. There's a lot of calculations of BPS indices where you take the M5 branes, put them on S1 cross S4, and then do some calculation in the 4-dimensional theory. As I mentioned, we think we can give some field theory explanation of these results using AGT. And then also going back to the supergravity solutions, there's many other things to calculate aside from the entanglement. And then also the more general question we'd like to study is, can we relate this definition of the central charge from the entanglement to other definitions, such as the thermodynamic entropy the trace anomaly, and so on. And so I'm done. Thank you.
So any questions, comments? Yeah.
The ADS3 cross S3 cross S3 solution corresponds to two overlapping M2, M5 systems, not to an M2, M5. And it seems to me this is definitely a different system than an M2, M5. So it seems to me what you computed the standard charge for the string on two overlapping M2, M5 systems, and then there's no reason to agree with any of the other computations, which are just for the M2, M5 system.
Yeah, there are some other M5 brains floating around. My understanding is you can get rid of those. Are you here?
But if you have ATS3 cross S3 cross S3, this is not what you get from an M2, M5 system. This is what you get from two overlapping M2, M5 systems.
Well, what you're saying is there's an additional parameter, which would be another number of M5 brains, which, as far as I know, we don't have in these solutions. These solutions only have, it's a subset, it's probably a subset of the solutions we're talking about.
I think it's different physics.
Okay.
Any other questions? Oh, over there.
Hi. Is there a way to look at RG flows with your formula? Some trivial way of like adding masses that would show monotonicity or?
Yeah, the short answer is I don't know. It's a question of what relevant deformations can you do on the string, on the self-dual string or on the Wilson surface, and I just don't know right now.
Okay, so let's move on the next talk. Let's thank the speaker again.
You spoke so long with your normal voice, I turned off the microphone. There is.